really one of the key contributors and deep knowledge about the language. In talking with Mark over the last year or so, I think between us sort of realized that there's this really interesting common set of interests between building secure systems, which is what Mark's interest is in, and building very small systems, which is what Maudible's interest has been in. And so I asked Mark to come and talk with us because the work he's doing that he's going to present, I think, really kind of embodies both of those, and also helps answer or provide a direction for answering one of the challenges that we face, where we want to be able to eventually safely run, effectively untrusted user code in JavaScript engines on embedded devices. And clearly the security concerns there are significant. The trust concerns are significant. So I won't say more. I'll just turn it over to Mark, and we'll go from there.
Okay, and just about to flesh out the background that you mentioned, I've been participating in TC39 since 2007. When I got started, the standard JavaScript was ECMAScript 3, and we were battling over whether or not to do ECMAScript 4, and ended up with ECMAScript 5 instead, which quite on purpose pointed us in the direction that makes the security properties I'm about to talk about possible. Okay, so I titled this talk, Omit Needless Words, because it's about this discovered alignment between the omissions that I've been trying to enable in order to create secure subsets of JavaScript and the engineering for running on smaller sizes, smaller size ROM and RAM especially for devices that Maudibile has been explaining to us, and our joint realization that so much of our engineering was aligned and pushing in the same directions. And I want to say that there's, while I'm still on the title slide, I want to raise, but not revisit really during the talk, that the issue of devices is not just aligned because of smallness, because of the need to occupy less RAM and less ROM. It's also aligned, I think, eventually, because insecure devices can kill us. This group, as I understand it, is about devices and wearables. Clearly, wearables are the first step towards implantables. We're going to be entering a world in which we'll probably all have lots of implantables implanted in us. And if they are operating at the security level of current computers, I think we should all be quite terrified. So the main methodology that I've been pursuing, I like to use the phrase, don't add security, remove insecurity. That the essential object computing paradigm that JavaScript embodies quite well, that object computing paradigm taken by itself is already a very good model of modular secure computation. The notion of memory safety, of object encapsulation, of invocation as message passing, where the receiving object reacts to the message only according to its code, and where it can only cause effects by using references that it holds. These are all perfectly aligned with the access control model called object capabilities. And the reason that our object languages are not good at security is because of all the additional stuff that's been added beyond the core object paradigm. So rather than adding a whole bunch of new mechanism for security, my emphasis has been to add means to remove the things that cause the insecurity and to remove them in an enforceable manner. So I'm going to take us through several subsets of JavaScript. So at the smallest subset is one that we're all familiar with, which is JSON, which is a tiny subset of JavaScript whose emphasis is only data, and it's become a universal format for safe mobile data. And part of what makes it universal is that it is trivial to parse, so no matter what the language and no matter what the platform, everybody felt empowered to go ahead and write their own JSON parser. Now, it's not quite trivial to parse correctly, so a lot of the massive adoption of JSON were by parsers that were slightly incorrect, but that's often the way massive adoption happens. On the completely opposite side of the scale, there's the full ECMAScript standard that was constrained to be upwards compatible with all of the legacy ECMAScript 3 stuff that existed at the time that I joined the committee. So it contains both strict mode and sloppy mode. And sloppy mode really is incredibly insane and really should be thought of as existing only as an ECMAScript 3 compatibility mode. With ECMAScript 5 came the definition of strict, which is a saner subset, in particular saner subset that enables the creation of the secure subset, the enforceable secure subsets. So the focus of the talk and the focus of our work at Agoric will be on SES, which stands for Secure ECMAScript, which takes advantage of the mechanisms introduced with ECMAScript strict and the mechanisms introduced into JavaScript standard since then, so that you can have multiple mutually suspicious featherweight compartments, confined boxes in which code can execute and in which mutually suspicious code can be put into contact with each other in a controlled manner so that each can protect itself from the misbehavior of the other. But to do so in a featherweight manner, because as opposed to, for example, with iframes or full realms, where all of these compartments are sharing one set of primordials, one set of global objects. And this fits very well with the constraints that the Moddable guys have explained to us of XS, where there in fact is only one root realm. In fact, SES does already successfully run within XS. And then I'm going to explain a very small subset of SES named Jessie, which is intended to be to serve a role like JSON, but for universal safe mobile code, to where Jessie is a sufficiently small subset of SES that, in the same sense in which everyone felt empowered to write a JSON parser in whatever language, Jessie is a subset such that it becomes straightforward to write a simple eval apply interpreter of Jessie, no matter what your language and what your platform, so that Jessie becomes a format for sending code with the security properties of SES, but easy to interpret on any target. The alignment with this group is that SES has a lot of the benefits that the Moddable guys have had directly on their radar with regard to freezing all the primordials, freezing many objects, reducing RAM footprint in that manner, but still with a ROM footprint for the ECMAScript interpreter itself, which is essentially the whole language, and a ROM and RAM footprint that supports a lot of the mutability of the language semantics, much of which is unnecessary for writing good code. So Jessie is also one that should reduce both ROM and RAM footprint significantly compared to SES. Before going on, I want to introduce two new terms which will be relevant for understanding all of this mechanism. XS right now has this notion of a deep freeze expressed in a non-standard manner. SES introduces two concepts, harden and pure, and they're very closely related to each other. They're sort of two separate concepts that together give you this notion that's like the notion of the XS deep freeze. Harden is for tamper-proofing an API surface. And it does it by recursive application of object.freeze, where object.freeze is not making something immutable, it's making properties non-configurable and non-writable, making the inheritance chain not mutable. But for example, when you do an object.freeze of a function that encapsulates mutable variables, the object.freeze does not prevent the function from mutating those variables. Now, so the way harden works is it's a transitive application of freeze that does its transitivity by walking properties, by traversing from property to all the things that are reachable just by property traversal, without invoking any of the functions of the objects being traversed. So it really is not about immutability, it is about tamper-proofing surface, so that between mutually suspicious objects, one subsystem can expose defensible objects to another subsystem. Now, under certain conditions, when you harden an object graph, you actually cause it to become pure. And what pure means is that this definition comes from the use in the Wyvern language. In Joey, we called it immutable. But what it means is that there is no mutable state or I/O anywhere to be found in that object graph. And therefore, that object graph is itself something that can be placed in ROM without needing the extra bookkeeping for shadowing those objects with mutations of those objects. Those objects are semantically have no encapsulated mutable state or I/O abilities, and that's no ability to either cause effects on the world outside, nor abilities to sense effects from the world outside. Okay. So now to take you through the subsets. The subsets nest. The subsetting that we, those of us who understand the JavaScript in some depth, the subsetting that we know well is the difference between the full ECMAScript standard versus the ECMAScript strict subset of the full ECMAScript standard. So the things shown in this Venn diagram between each contour, between the ECMAScript box and the ES strict box, are all of the things omitted from ECMAScript to get to ES strict. And so that will be following that graphical pattern throughout. And we're also using horizontal versus vertical. I don't know if you guys can see this based on where the zoom control is, but the horizontal arrow at the top of the screen is labeled semantics, and the vertical arrow on the left side of the screen is labeled syntax. So we're going to be using horizontal and vertical in order to notate the difference between semantic subsetting and syntactic subsetting. So the full ECMAScript standard contains with, that's a syntactic element that is statically omitted from ECMAScript 6, I'm sorry, from ECMAScript strict, and the full ECMAScript standard contains the crap on the right that I won't go into unless anybody has a question, but those are the elements from sloppy mode that are omitted to make ECMAScript strict mode. So zooming in, what are the things we omit from ECMAScript strict to make secure ECMAScript? And it's really three main concepts. One is this issue of the primordials. Let me define primordials. Primordials are all of the objects that are mandated to exist before code starts running, except for the global object. For reasons that will become clear, we omit the global object itself from our definition of primordials, but object, array, object.prototype, array.prototype, array.prototype.push, and all of the other method objects. So that whole object graph of objects that exist before code starts running, those are all primordials. And when, according to standard ECMAScript, including ECMAScript strict, those are all mutable. Those can all be mutated. And therefore, the XS engine, when just running standard JavaScript, has to pay tremendous bookkeeping overhead to enable any of them to be mutated, even though almost all programs never mutate any primordials, in which case all of that bookkeeping is essentially wasted space and wasted time. To go through the extra bookkeeping every time you access a property is also costly of runtime. There is, for the realm as a whole, a single global object that contains, so that's the per realm global object at the bottom, and that contains both the ECMAScript standard primordial globals like array and object and function and JSON, etc. But it also contains host-provided globals like in the browser, window and document, an XML HTTP request, in Node, process and require, and then through require various modules that give access to the file system. So these are basically sources of authority, sources of the ability to cause effects on the outside world, which all code has access to. And because all code has access to it, it means everything is vulnerable to all code, that there's pervasive vulnerability. And therefore, every time you build an application in JavaScript for any hosting environment, and this includes, in the current status, the embedded with XS. In the current situation, all of the authority that is provided by the host by populating the global object is available to all code, including all third-party libraries that are being linked in, because they all have that global scope in scope and can name any of those objects, which are the ability to cause effects. So removing those concepts, so let's take a little detour. So this is an example of some of the primordials. There's a particular subset of the primordials that we distinguish, which are called the undeniables. And we distinguish them because they're reachable by syntax. So no matter how initialization code might try to change the primordial namespace before freezing it by replacing object or function, or replacing object.prototype, array.prototype, etc., code by using literal forms, an object literal, a function literal, and an array literal, can directly reach things like array.prototype, object.prototype, etc. So those cannot be denied by simple monkey patching, by simple customization of the primordial object graph. The global object is the one that has the bindings for the elements of the primordials that have global names. And then among the primordials, we distinguish two particular kinds, which are the evaluators, which evaluate code in a scope where the free variables in that code, the variables that are used in the code but not defined in that code, are instead looked up in the global object. So evaluators are scoped to some global object. So with those concepts in mind, let's return to our subsetting diagram. And if we remove those three concepts from ECMAScript strict, we end up with secure ECMAScript. So where ECMAScript strict has mutable primordials, secure ECMAScript has pure primordials. And what I mean by pure, we cause them to be pure mostly by applying harden. But one of the things that we've done over the entire time, starting with ECMAScript 5, is, with the exception of a very small number of grandfathered bits of implicit mutable state, which we can ignore for present purposes, with the exception of those grandfathered bits, we have constrained the primordials so there is no hidden mutable state, such that if you harden the primordials become pure and therefore ROMable. Secure ECMAScript has all the primordials are pure. And instead of having one global object for the realm as a whole, rather we have an ability to create compartments where each compartment has its own global object. So let me, by way of notation, mention that I'm using underbar in the subsetting diagram for new concepts that this talk is introducing that are not concepts that are already present in ECMAScript itself. Um, Another concept that we will be introducing with a separate proposal. It's a proposal that fits with SES. It has a natural synergy with SES, but it's a proposal that stands on its own, which is defensible classes. That's going to be introduced with the @def decorator. For those who don't know about decorators, I won't explain them here, but the point of a defensible class is, again, a hardened API surface. A defensible class is like a normal class, except the constructor, the prototype, all the methods on the prototype are all frozen. So the transitive API surface of the constructor itself is hardened. And in addition, the instances made by the class are hardened. That does not, for the class as a whole, if there's no hidden static state, which is typical for classes, hardening the class makes the class pure. For the instances typically do contain, or typically will contain, hidden per instance state. So hardening them tamper-proofs their API surface, but does not make them pure. So the instances typically will not be ROMable, but the classes themselves will be. So in SES, we initially defined this through the original Frozen Realms proposal, where the primordials start out frozen. And what we found was there is one kind of code which does exist and is important and is now considered to be code which is part of best practice, which are shims that run ahead of time and customize the environment. So the way we currently define I'm not going to distinguish SES and Frozen Realms. There's the Realms proposal, and then Frozen Realms and SES are now merging. But SES is defined such that vetted shims, trusted shims, can be run ahead of time prior to freezing all of the primordials. And I was very pleased to read recently about the XS preload logic, and this is almost identical, and I think they can be mapped onto each other rather perfectly, where the shims are run without access to any external mutable state or I/O devices. They're run confined, and once they're done, and therefore they can all be run at build time in a device environment rather than at runtime. And then the resulting primordials that result from that customization can then be snapshotted, placed in ROM, so that only the things that are different afterwards become the things that need to reside in RAM. So now I'm using the gray background to indicate the objects that are placed in ROM. So in this case, the full set of primordials are placed in ROM, are completely frozen and pure. And the objects that don't have the gray background are in these yellow boxes, each of which is a compartment. So each compartment has its own per compartment global. The evaluators for the compartment, the eval function and the function constructor, evaluate code only within the scope of that compartment's global. And these compartments all inherit from the same set of primordials, so the code loaded in different compartments can be put in contact with each other and interact perfectly well. And if they harden their API surface before they're put in contact, they can also defend each other from each other's misbehavior. Even when a hardened object is not pure, I want to emphasize that that itself reduces the need for runtime bookkeeping, because the data properties are now only writable. They are not configurable, and therefore there's much less bookkeeping needed in order to provide for the runtime representation of a non-configurable mutable data property. Likewise, a function that a non-writable, non-configurable mutable data property that holds a function that encapsulates state. Once again, it's not placed in ROM, but there's much less runtime bookkeeping that should be needed. Okay, so back to our subsetting diagram. So the elements that are in the yellow or the light green are the elements of secure ECMAScript, which enable tremendous amounts of existing JavaScript code that obeys best practices to run as SES code. And the experience both at Google with Google Kaha, which contained the earlier version of SES, and today with Salesforce that is running a 5 million developer ecosystem on top of the modern version of SES. Both of those experiences, and as well as our experiences so far at Agoric, which granted are currently at a much smaller scale, but all of those experiences verify that leaving aside trusted shims for doing a pre-freeze customization of the environment, that aside from those, a tremendous amount of existing JavaScript code that obeys best practices runs in SES and therefore can be separated and protected from each other through the means already explained. Now, Jessie is intended to be a tiny subset of SES that is not intended to support existing legacy JavaScript code. So all of the elements in yellow and light green, we remove them to make Jessie, and that includes some elements of the SES runtime, including property reflection, various things that make implementing ECMAScript burdensome, and most radically of all, secure ECMAScript has this and new and instance of, as well as classes, all of which is in support of defining objects by inheritance, and the support for mutable properties. We omit all of those concepts to make Jessie. So in Jessie, all objects are hardened. All properties of all objects are non-configurable, non-writable, and all modules are pure. And we'll come back to the modules in a moment. In the absence of inheritance, the pattern of objects that we're using is something called the objects as closure pattern. So Jesse code is not allowed to count on any of the things outside the Jesse box. However, there's a bit of a definitional oddity in the definition of Jesse, which is Jesse is purposely a subset of SES. So we define the Jesse language such that a correct Jesse program must remain correct if run as an SES program within an SES system. And therefore, a correct Jesse program may not count on the existence of the full SES runtime, the elements that are outside the Jesse box, but neither may a correct Jesse program count on the absence of those things. And therefore, a defensive Jesse program must defend itself under the assumption that the adversary might be coded in SES, but still under the assumption that the adversary is coded in no more than SES, because SES provides all the restrictions needed such that Jesse objects can protect themselves from SES objects. And therefore, Jesse code can run on incredibly tiny standalone Jesse interpreters, but they can also run within a full SES environment without needing to introduce any mechanism to distinguish Jesse from SES. So, removing the syntactic elements of SES, most of which were either in support of inheritance or, like switch fall through, was just a footgun, just something that was accident prone and something that good code should avoid anyway. What we're left with is Jesse contains JSON, and therefore it contains strings and objects and arrays, null, true, and false, numeric literals. Beyond JSON, it contains, as I mentioned, pure modules with import and export that we'll come back to in a moment. It contains most of the operators, and pointedly, it does not contain double equals, but it does contain triple equals, because once again, double equals is just makes code unreliable and should never be used by code following best practices. Strangely, Jesse omits proxy itself because proxy is hard to implement, but proxy and weak map were introduced into JavaScript in order to support the creation of membranes. So Jesse, while omitting proxy, will directly have, as part of its available runtime, a membrane library, because that is very supportive of security patterns. And in a standalone Jesse environment, where all objects are hardened, the subset of the membrane concepts which are meaningful in a standalone Jesse environment are easy to implement. So all of these things should admit to a fairly straightforward eval apply interpreter that can be essentially ported to many conventional imperative memory-safe object languages by writing a simple eval apply interpreter. And Michael Fig is collaborating with us and has created a project called Jessica, which is a self-rehosting meta-interpreter of Jessie in Jessie, and he's already partway through using it to do a rehosting of Jessie into C, but without yet having done the C runtime elements needed to support Jessie objects within a C system. But that gives, I think that gives a very good sense of, if you take a look at what he's doing, it gives a very good sense of how tiny the subset of XS would need to be in order to create an XS that supported only Jessie. So returning to our concepts of harden and pure, in order to explain our modules, we need to, the modules admitted into Jessie, as well as most of the modules that will be useful in SES. The key thing is to write modules in a form that is statically verified as purifiable. To actually harden every exported value of every module by explicitly using harden, even though harden is a very nice abstraction over object.freeze, it is still notationally awkward. Sufficiently notationally awkward that programmers will resist putting in the necessary hardens, and it does create a readability burden. So instead, we define this notion of purifiable and a notion of a pure loader. So modules export and import, and a pure loader is one where, in order for a module to be loaded by a pure loader, the module has to have passed a static verification that it is purifiable. And what purifiable means, I'll give the definition first and then I'll unpack it. What purifiable means is under the assumption that everything the module imports is pure and that everything the module exports is hardened by the loader, that the consequence is that everything the module exports is actually pure, and therefore any other purifiable module importing from this module is importing only pure values. So now I'll unpack that. So export function make point. Make point is just a function as interpreted by a normal ECMAScript module system and module loader. Make point is not hardened, it is mutable, and therefore it is not ROMable. However, the modules are the wiring between modules, between the imports of one being wired to the exports of another, goes through a loader, and the loader can intervene on the values that it's wiring from one module to another. So without any further explanation, we can see that make point itself, if hardened by the loader as an exported value, becomes pure because the function closes over no assignable variables, and in this case, it closes over no variables. Harden itself is understood as a special case by the static checking. If it did close over any variables, we would need to ensure statically that the variables were not assigned to, and that the variables were themselves initialized only to pure values, not to purifiable values, but to actually pure values. Now, this function, when invoked, will return a hardened object, but not necessarily a pure object. That does not prevent the function from being placed into ROM. Now, at the bottom, we import the value xx from a foo module, since the assumption is that we're being loaded through a pure loader that enforces that it's only loading purifiable modules and it hardens all of their exports. We can assume here that xx itself is a pure value, and then through our static checking rules, in this case, and this is where the static checking rules get admittedly delicate, we can, because make point is defined within the same module, we can, in this case, verify that if both x and y, if both of those values are themselves pure, that in that case, the instance, the hardened instance returned by make point is itself pure, and therefore the export const pt at the bottom still passes our static check that that point instance is purifiable. If we were passing into make point something that was not statically known to be pure, then we would not know that the point instance being exported was purifiable, and therefore this module as a whole would fail the static check, and a pure loader would refuse to load it. And I think that is the end of my prepared talk. There's lots and lots of concepts here, and I'm now prepared for questions and discussion.
Thank you, Mark. That was a lot. Oh, it's great. I mean, it's good. It's the third or fourth time I've been through this material in various forms, and I'm starting to feel comfortable with it. It's a lot. We should open it for questions. You and I have had a chance to discuss this stuff before, but other folks may have something to say.
Are there any? Sorry. I think one of the things I've liked about the work that I've witnessed the last 2 days, and just as I read up on your October minutes, I think what's made this group so effective is that where there's an existing industry metaphor paradigm that can be applied, that is easily understood, universally understood, both in context and syntax, to adopt it. And my question is how consistent is this in approach, and is there a competing approach that you would consider for security?
So there are a lot of claims out there. I have enough academic papers and various talks that are recorded and up on the web, and lots of other material that I can cite, that I feel comfortable now simply making the strong claim that there is no competing approach to the approach taken here that provides anything like the level of security that this provides. Now, this is not uniquely so by the approach, what I mean is the object capability approach. So in particular, the transition from ECMAScript strict to SES, that there are many other approaches to security that have tremendous things to say to them. Now, some of those can be combined with object capabilities, and SES is not uniquely the only way to get from ES strict to object capabilities. So with regard to a lot of the particular design decisions to get from ES strict to object capabilities, there's a design space there. And we made a bunch of choices. I am not aware of anything out there that is trying to provide object capabilities for modern ECMAScript strict, which is a competitor. The key phrase in there was modern. The old SES in Google Kaha was defined mostly as a object capability subset of ECMAScript 5 and has led to other work. And both it and some of that other work does show somewhat other ways to get from ECMAScript strict to SES, but nobody has attempted to reproduce any of those for modern JavaScript. So that was a long way of saying, no, there's realistically nothing competitive with this. And we are pursuing this through the Realms proposal and then following it with the SES proposal, which is what Frozen Realms is mutating into. So that's all standards track. Separately, we will be proposing Harden as a standalone proposal that can be used both inside and outside of SES, as well as defensible classes as a standards track proposal. And this follows a long tradition. Most of the elements that we've used to get to where we are, including promises and proxies and weak maps and et cetera, were already introduced standards track in order to enable the building of SES.
Mark. Oh, sorry. I think this is a really great thing you've got there, and I can see lots of applications of this. I've got far too many questions to ask in a few minutes, but probably the highest level question would be, how does this interact with, so what you've got here seems to be protecting some JavaScript code from, or some not quite JavaScript code from invading another piece of code within the same realm. And I'm wondering how this interacts with the case where you've got some code that you want to access, you want to enable it to access particular I/O devices, say through an import or something like that, and then another piece of code that you want to either enable with different I/O access or you want to restrict I/O access. So that the way you've described it, it seems like you're restricting access to globals, but what about imports? And especially in the case of I/O imports, that would be not hardenable by definition, I think.
Okay. Excellent question. Any object capability system has to solve the problem of where does initial authority to the outside world come from, and how is it propagated through the system in a safe way. I put pure modules into the Jessie box, but not the the SES box supports modules that are not pure. We're working now but are still in a per compartment basis. So we're working, this is work in progress with the SES group that Salesforce and Node and GoDaddy and several other players are all participating. MetaMask in this SES group, and our main topic is the safe module system for wiring up and propagating through initial authority in a way that enables the programmer to express least authority. So there is this famous recent incident called the event stream incident, where a module known as event stream, a package, an NPM package known as event stream, was changed by the person who inherited its maintenance, was changed to be malicious in sneaky ways in order to steal the Bitcoin of an application that was linking in that module. And that was necessarily easy in current JavaScript because of the pervasive access to the genuine global object and therefore to all authority. This is our test case for designing a system that can support legacy code and provide individual modules and individual packages with least authority. So the way we do that is partially through a manifest that says how different packages can be wired to each other, which is basically a constraint on the import graph, as well as a partial redirection of that import graph. So very concretely, if module foo does a import or a require, I'm not going to distinguish import and require because we're looking at node code right now. So things that are expressed that would be expressed in import are currently expressed as requires. So something that requires FS, the manifest can redirect that through an attenuating module that imports the real FS and exports an attenuation of that FS that presents the same API but gives access to only a subset of the files. Likewise, the per compartment globals, you can redirect the definition of the values of global variables through attenuating modules as stated by the manifest. So the manifest can work with legacy code, but the basic idea is that each compartment becomes a separate protection domain that is populated with the least authority needed by the package loaded into that compartment. And then you express constraints on the allowed import graph so that basically each compartment has its own global as well as its own loader. And the loaders of the compartments know each other and enforce the constraints, as well as this rewiring through attenuators. And the result is that other than writing new attenuating modules and writing this wiring manifest, most of the rest of the code can be legacy code. In addition, Bradley Meck of GoDaddy and Node is working on a tofu tool, trusted on first use, to automatically generate the information needed to generate the initial manifest and attenuating modules so that you can start off with attenuations that provide the packages with what the authority that they currently seem to need, but no more, which in the case of the event stream incident would have caught the the malicious upgrade of the module to use authority that it didn't previously need to use and was not previously using.
Thanks. That was very clear.
Yeah, and we will be making I can forward to this group the current draft of the SAFE module proposal, but keep in mind that it is rough, and this working group is continuing to work on it.
Well, one reason I'm interested in this is this whole evolving larger JavaScript ecosystem with browsers, Node, and everything. But what other efforts outside this ecosystem are there for this kind of portable, safe code? And what other environments are there?
I'm sorry.
Version of the competition question.
So we're talking to, let's see. So Salesforce is currently using it in the browser. Agoric, my company, is, as well as MetaMask, who are participating in the working group, are both looking to use this in the blockchain ecosystem. In the case of Agoric, we're looking at it in a node-like manner to run on the server side on top of blockchains themselves. In the MetaMask case, they're looking at it primarily for the browser side for creating a secure user interface system for interacting with distributed applications that are themselves running on existing blockchains. We're talking to Bradley, as I mentioned, about using all of this directly on Node, and and that's what it would take to address things like the event stream incident. We're getting a lot of interest in being able to write server-side code, node-side code in a more robust fashion, which this would enable. And we're talking to Brave about a multi-realm manner that in a more radical, in a more extreme fashion, enables legacy code to be secured by combining the SES mechanisms with the full realm mechanisms, where you create multiple confined realms which are not frozen, but which are only given least authority, and put between them security enforcing code that is itself created in an SES realm and therefore can protect itself from malicious code on both sides. So it allows the mutually suspicious code to be full non-defensive legacy code, but interacting with each other only through new defensive SES code.
Okay, I appreciate this. I think that there's a longer discussion on portable code and things I'm interested in, but my question is other languages and other environments that are trying this kind of thing.
Okay, so non-JavaScript.
Non-JavaScript.
Okay. So at the fine-grained per object level, there's very little happening in industry for object capabilities at a parser level. There's a lot going on. Basically, something more like what I described as the Brave use case, where you have or an operating system like use case, where you've got processes interacting with each other by object capability rules rather than conventional rules. The SEL4 is a extraordinary, secure, high-performance operating system built by object capability principles, in fact, very similar object capability principles. And it is the only, today, it is the only practical secure operating system that has been verified correct. For a very, very different example, there's Cap and Proto and the Sandstorm ecosystem built on top of Cap and Proto, where you've got processes in Docker-like containers. They have their own container mechanism that's Docker-like, but where they talk to each other through the Cap and Proto protocol, where the Cap and Proto protocol both has a protobuf-like serialization for serializing objects by copy, but has exactly an object capability protocol for invoking services. And that's actually based on my previous work on CapTP, which we're redoing also for SES in order to create a distributed SES.
Okay. Yeah, we don't have time to talk about it. I'm very interested in continuing this when there is time, because these are topics I'm very interested in. But I'll give this back to Peter for now.
Okay.
So, Mark, I wanted to ask maybe a slightly practical question out of all this. I was interested particularly by your comment that you have some experience with SES in the wild through Salesforce. And if I recall well, what you said is that you characterized it as the majority of kind of well-written code.
Not the majority. And if I might have said that or implied that. But let me backtrack from that. It's a tremendous amount of existing code written to recognize best practices. And when I say recognize best practices, I'm speaking of already recognized rather than something we're proposing to be new best practices. So the primary best practice, primary two best practices is all of your code should be strict, and you should not monkey patch primordials. And that's why I had to exempt shims. Shims are the one case of mutating primordials which are considered to be within current best practices. So leaving those aside, code that is written only to strict and which does not mutate primordials, a tremendous amount of that code is already SES compatible. And it might in fact be the majority. I just don't have any measurements to justify making a claim that it's a majority.
Okay, that's fair. I think the clarification is helpful. So where I'm going with that is this committee is embarking on what is effectively a new target, and so we have, I can safely say, relatively little legacy code compared to the web to deal with. And so there's, as you were talking, the question sort of arose in my mind. If we optimistically assume that SES exists, down the road as part of the standard, should we as a group be thinking, gee, maybe SES should be the default runtime model that we target for devices? And you did a wonderful job in your opening slide of adding the word implantable to scare us all to death about how serious the work is. Do you think that SES is sort of an appropriate, given this, still somewhat nebulous, or not fully defined, not nebulous, do you think that's something we should be looking at or considering as a reasonable baseline target for delivery of the work that we're doing?
I do. I think for a new platform where you're not burdened with a tremendous amount of legacy code, that everything that's in JavaScript that's outside of SES, I think for a new platform is useless. And I'll make that statement unqualified. In addition, going back to the terror of implantables, let me mention another design point of Jesse, for which we're working on it, but it's still too early to make strong claims. is Alan Schmidt on the committee from the JS CERT project in INRIA has done this extraordinary, well, the whole JS CERT project has done this extraordinary work doing a mechanized formal model of JavaScript as a whole. SES includes most of JavaScript, so a mechanized formal specification of SES as a whole would be somewhat smaller, but would still be most of the size of the mechanized specification of JavaScript. And even though he has a mechanized specification, because of the complexity of JavaScript, it has to be a low enough level specification that it's not very useful for proving security properties of realistic code written in JavaScript or SES. One of our design targets, a very important design target, especially for us in the blockchain world, is we intend to write all of our smart contracts in Jessie and to recommend to our users that they write their smart contracts in Jessie, even though we provide them all of SES, so that we can support formal analysis tools that can give you a static verification of interesting security properties of code written in Jessie. We're working with a group of academics, I'll just name drop, Sophia Drosopoula, James Noble, Toby Murray of the SEL4 project, on a specification language called chainmail that assumes an abstract object model as its code model of what it's proving properties about, and is really focused on the mechanism of specification and proof, but we believe that it can be composed with Jessie eventually in order to provide mechanized proofs of interesting security properties of Jessie programs.
Okay, excellent. So, I mean, it's an intriguing, backing up a little bit, it's a very intriguing thought that that there may be a subset that's an appropriate one for us to look at. I think we all have some homework to do just to catch up on what that would look like in the implications, but very much appreciate the introduction today. Rick, you were holding something up to the screen and I didn't look soon enough. I just wanted to check if you had anything you wanted to add before we closed out this topic.
Oh, my notes that I took during Rick's talk, I wrote down, should we require strict mode? Then I wrote, no script target, only a module target. And then eventually I wrote SES and put a big circle around it. For exactly the reason, Peter, that you said. It's very nice to be able to unburden ourselves from the 1JS doctrine, right? Which is to say, like, we're not going to like disable, break things that have existed forever because there's this world of code, extant software that must continue to run properly on some bank somewhere in some time that would be a disaster if we were to break it in our efforts in TC39. We don't have that burden in TC53. So it seems to me that we should take the opportunities to create a both expressive platform but also secure platform. And as I said yesterday, I've been on TC39, a delegate to the committee since 2012. So I've been working side by side with Mark in that time, and I've come to have a great deal of respect for the work that Mark does, and more importantly, the approach, the strategy that he takes, which was summed up very nicely in a slide that you had early on, which was don't try to make security take away insecurity. I think that's brilliant. See, I'm really all into this, and I love the idea of we don't even have to worry about Appendix B.
Yep.
You know what I mean? Like just like even if it turns out that like obviously we need to experiment with this, like put it out there. We're not going to make any decision rashly or prematurely, but I would say that even if we find ourselves in a position where like maybe it's too restrictive for one reason or another. Now, I'm not saying that is even a scenario that we will encounter, just hypothetically. I see no reason why we couldn't and like make rules that say strict mode only. You know, like this, we have the authority to do that, and we have the authority to write tests for conformance of that.
Rick, thank you very much. I appreciate all of that tremendously.
You're welcome. And thank you so much for doing this talk today. This is fantastic. I actually hadn't seen this one yet.
This one's new.
Mark, can I also ask you a question? So this is Ishtan. This Jesse, is it already also at TC39 or not yet, or it will never come?
It is not yet stated in a manner appropriate for bringing as a proposal, but I would love to bring it as a proposal. With regard to, for Jesse itself, whether it should go to TC39 or TC53 or somewhere else, I don't have a strong opinion on that. So your advice is solicited. But the natural thing for me, just based on my history, would be to bring Jesse as a proposal to TC39.
But you said that it is not compatible with the rest of the onion, yeah, which is outside.
It is not compatible with existing JavaScript code. It is a subset of the outer parts of the onion. So anything written in Jesse will run as SES, and any correct Jesse program by the peculiar definition of correct Jesse will still run correctly when run as an SES program. We have that direction of compatibility, but there's essentially zero existing JavaScript code which will run as a Jesse program.
Okay, so then I have a last question, and then probably also the time is over. So practically you are restricting yourself as you go more inside of the onion.
Yes.
So is there any issue regarding performance or any other restriction that, for instance, when you have a code with Jesse and in comparison with a code which is outside in the onion, but it is not so secure?
So I'm sorry, did somebody else have some? Was somebody else saying something?
No.
Okay. We're currently using the Realm shim both at Agoric and at Salesforce and at MetaMask. For the shim, we're encountering two sources of overhead. One is that the mechanism we're using to intercept global scope references so that we can do a per compartment global object is a with on a proxy. And we're doing a mechanism to make that efficient in the typical case. But when there's this optimization mechanism, but when a global variable reference misses the optimization, misses essentially the optimizing cache, which happens quite often, there's a substantial overhead of going through the proxy mechanism. With SES directly supported by the platform rather than as a shim, that overhead goes away. The other source of overhead is the override mistake. That is irritating. It is not so irritating as to be a impediment to practical use. Salesforce is in deployment with paying both of these costs, and they're not finding either of these costs to be an impediment to practical use. There's a proposal before the TC39 committee to fix the override mistake in the standard. And if that happens, then that source of overhead goes away. However, it's not known how web compatible that is. If in TC53 we can somehow allow ourselves to run SES with the override mistake fixed, then again that should have no cause of overhead. So taking care of those two, there's one remaining source of overhead that's worth calling out explicitly, which is the objects as closure pattern for expressing objects has an allocation cost and therefore a RAM cost, so it's quite relevant to this committee, where you have to allocate a closure per method per instance. Now, my E-language and a previous proposal that I had made to the ECMAScript committee back in the transition days from ECMAScript 5 to ECMAScript 6 shows that it is possible to implement objects as closure without that space overhead, but it requires some re-engineering of the object runtime. With current object runtimes, you have the allocation cost of a method of allocating a closure per method per instance. That's significant RAM. It is not significant runtime for object abstractions that are written well, but that's a weighted definition of well. What I mean by written well is object abstractions that don't have a tremendous number of methods in the equivalent of a single class, but rather have lots of small classes, each of which have small numbers of methods.
Excellent. So again, thank you, Mark. It's tremendous to have an opportunity to hear you present this and get the ideas kind of firsthand from you in front of this group. And good news for you, our next meeting in 4 months is scheduled to be in the Valley, so we may be able to follow up in person.
Great.
But anyway, I'm sure we'll be talking in various forms between now and then. So thank you.
You're welcome. Thank you for inviting me to do this. This was a wonderful opportunity. And thank you for letting me record.
Yeah, Patrick will follow up. We should get the presentation to put in the notes and share with other folks as well.
Okay, great.
Great. So we ran a little long, which is fine. I want to take a break until 3:30 when we'll reconvene, just because I need to stand up and stretch for a few minutes before we keep going.
Okay, so I will stop the recording and sign off.
Thank you.